Okay, folks, so what we'd like to do now is look at integrating not with respect to x, but with respect to y. So rather than integrating with respect to x, we're going to integrate with respect to y. So now what I'm going to do is, remember before when I drew my dx thin rectangles, each one of these rectangles had a thickness of dx. I'm now going to slice it the other way, and I'm going to slice it so that each one of these rectangles has a height corresponding to where it intersects the function. So this rectangle that I just drew right here has a height right there, and this rectangle right here has a height that's this functional value right here, so whatever that x coordinate is. But I'm going to label I'm going to think about the thicknesses of these. If you were to zoom in on these rectangles, I'm going to think about their thicknesses as being dy thick instead of dx thick. Okay? So what we can do is we can actually start all over with calculus, with integral calculus. We could start all over with a Riemann sum and integrate not with respect to x, but with respect to y. So here we've drawn several horizontal rectangles, all with a small dy thickness, and look at how we then represent the net area. Okay. Small typo, folks. I'll correct this for your notes, but that should be gy. So we've got g of y. Now notice what this function is here. This function isn't a function of x, it's a function of y. We're treating y as the independent variable. So in fact, we would write it as x equals g of y. You input a y value, and it outputs an x value. Okay. So here we're asked, or if we're asked to compute that net area, we would go ahead and give this expression right here. Okay. So, for example, the above function is f of y equals this expression here. Go ahead and represent the area as a definite integral of y, and then find that area. So this definite integral is going to be the integral from not x equals 0. We're not going to integrate from x equals 0 to x equals 9. That's what we were doing if we were integrating with respect to x. Instead, we're integrating here with respect to y, and our smallest y value is y equals 0. And our largest y value is up here at y equals 9. Now careful, folks, there's a little bit of coincidence here that the number 9 showed up twice in this problem. But this is the upper limit of integration. This is the lower limit of integration when I'm making my rectangle stack up like this. So we're going to integrate this from y equals 0. Be very careful here, folks. I'm writing that as y equals 0, not x equals 0, up to y equals 9 of our function, minus 4/9 y squared, plus 32/9 y, plus 17/9 times differential y. And there we have the way we will integrate, not with respect to x, but with respect to y. Okay? So I'll let you go ahead and finish this problem out. So you need to go ahead and compute this. All right. So I'll pause the video while you do, or you pause the video while you work through that, and then we'll move on to the last problem here. Okay, for number 20, we want to go ahead and find the area of this shaded region, not by integrating with respect to x, but with respect to y. So this is a really important skill to get used to, folks. If I were integrating with respect to x, I would draw the regions like this. I would go ahead and draw my dx slices like this. Don't jot this down. I would draw, these would be my dx thick slices. But instead, I want to integrate with respect to y. Let me first ask, why would we want to integrate with respect to y? Well, look what would happen if I did integrate with respect to x. Similar to one of the problems you worked on the previous page, notice that here my upper function is red and my lower function is red for this particular rectangle. But eventually, my upper function will be red, but my lower function will be black, and I'll have to enter two integrals to be able to evaluate that, and that could be a pain. There's other reasons why you might want to integrate with respect to y as opposed to x, and you'll sort of explore and learn those just through intuition after you've worked a lot of problems. But we're told to go ahead and integrate with respect to y. So let's go ahead and now, this is what I do want you to write out. Let's go ahead and draw some of our dy thick slices. These are our dy rectangles. They're very, very thin rectangles. And this is the height of that thin rectangle, represented by the distance between those two bars that I just drew. And here's the height here. So how do we go ahead and integrate with respect to y? So we're going to do the integral from our lowest y value on here. So careful here, I'm not doing with respect to x. My lowest y value is this y value right here, whatever that corresponds to. And my highest y value is this y value up here, whatever y coordinate that corresponds to. So we need to find these two intersection points to be able to answer this question. So let's go ahead and take the first function, y squared minus 3, and set it equal to the second function, 2y. That gives us y squared minus 2y minus 3 equals 0. And that happens, let's see, we could factor that. That happens at y equals 3 or y equals negative 1. So we see that's the y value, negative 1 there, and here's the y value, 3. So again, I'm stacking up these little rectangles here. We're going to go from y equals negative 1 to y equals 3. And now, what do I want to think of as my integral? Well, rather than saying I want the upper curve minus the lower curve, I want to think of the width, or excuse me, the total, I'm going to keep using the word height here even though I'm drawing it from left to right. That's my height. So this is the top of the rectangle and this is the bottom of the rectangle. Let's do it again. There's the top of the rectangle, there's the bottom of the rectangle, and its thickness is differential y. Let's go ahead and put that down. So which curve represents the top? The top is represented by the black curve of 2y, and the bottom is represented by this parabola. And if I want to find the length of this, the height of this rectangle right here, let me do it one more time now in red. If I want to find that distance right there, I'm going to take the top value, which is 2y, and subtract from it the bottom value, which is y squared minus 3. Careful, I do need those parentheses there. So now we can go ahead and evaluate this integral. But what did we do? Just to reiterate, what we did was we did the y value that was smallest. So let me go ahead and even put, it was the lowest y value on here, to the y value that was the upper y value on here. So again, that was our smallest y value for this region was minus 1. The largest y value for this region was 3. We found that by setting the two curves equal to each other in this case and finding their intersection points. Okay? So we did the lower value up to the upper value, and then we did the what? We did the right curve minus the left curve integrated with respect to y. Okay. So let's go ahead and do this. Evaluating this integral, we get, let's see, the integral from minus 1 to 3 of negative y squared plus 2y plus 3. We're integrating with respect to y. When we do so, we get minus 1/3 y cubed plus y squared plus 3y. And we're going to evaluate that from y equals negative 1 to y equals 3. And let me just let you finish. Okay, so I'll let you finish that out. But that's how we integrate with respect to y, and in some cases, integrating with respect to y will make our lives quite a bit easier. All right, we'll go ahead and stop now, and we'll pick up the last bit of information on the next page. Okay, folks, all I have here is a summary of what we just looked at. When we're integrating with respect to x, we go ahead and write from x equals our left value to x equals our right value, and we do the upper curve minus the lower curve. Remember that expression upper and lower has nothing to do with where the x-axis is and has everything to do with which curve is giving larger, more positive functional output values than the other. Okay? So even if I was dealing with two curves down here in this region below the x-axis, I would still go ahead and say that on this interval, this is the upper curve, because its y values are more positive or closer. They're on the number line. They are to the right of these y values down here, and we would call this the lower curve. So it's always the upper curve minus the lower curve if we're integrating with respect to x. If we're integrating with respect to y, we would often have a region that would maybe look like this. Here we'd have this. Let me make that a little bit nicer. We would have this curve right here and this curve right here. And so I'm going to call this the right curve because its functional values, remember these are for thinking of x as the output, y as the input. These output values more to the right than these do, and this would be the left. And so that's how we would go ahead and set up the integral when integrating with respect to y. We would start off with our lower limit of y value up to our upper limit, so that's lower to upper that we just did there. There's lower, there's upper. and we would do the to construct our dy slices. There they are. And what are the heights of those dy slices? They are the right value minus the left value. So there's a nice summary of what we just did. And now I'd like you to try number 22 on your own. There's just a minor error on number 22. Actually, I guess there's two errors that you'll spot. One is that this is integrated not with respect to. This should be integrated with respect to y, so you'll have to change that. And then take a look at this and see if you can spot the error and then correct it for number 22. And that finishes up the last pre-work of the last assignment. Congratulations.